Hi everyone, I'm Daniel Botero Lopez, and I'm a civil engineering student from the University of Maine, and my advisor is the Professor Aaron Gallant. So my research topic is called Global Stability of Column Support Embankments. The motivation is that these columns are very popular because they accelerate construction by reducing stresses in the subsoil. There are some vertical mechanisms that allows this, and for example, one is the arching mechanism that transfers the load of the field to the columns, and then the remaining soil will generate some deformation in the soil, and compared with the deformation of the column, will generate some down drag. And finally, the stresses in the tip are transferred to the more competent soil. So this mechanism helps to alleviate this method, these stresses, also helping with the global stability and also protecting adjacent structures. So this is a very important construction method to improve the soil or to alleviate the stresses. But the problem is that normally the FHWA they don't account for this mechanism and this alleviation of stresses. For example, as you can see, this is the method of slides, where the field height of each slide is considered the full weight of the field and also the soil. So this doesn't account for that and ignores the physics of the system. So the methodology to assess this is, okay, let's first focus in assessing or trying to calculate well the stresses in the soil. So for doing that, we have this procedure, and it's just putting the stress due to the arching, which is the SRR, and it's the stress reduction ratio. And then try to input the formations, try to use also a stress compatibility of the time, because the load cannot increase or decrease. And also compute the formations, compute relative formation, and using these interface expressions in which is very common for a TC analysis, for example, for geotechnical engineering, and also this QC, we can estimate how much load there is remaining and how much load is getting the soil, the interface, and it's transferred to the column. So this is our mechanism to calculate the stresses. And second, we perform a parametric study, like 135 cases. And we can see here, for example, these are 3 simulations for different column spacing. That the column spacing goes smaller, we can see that the failure surface decrease, the depth of the failure surface. So this helps us also to simplify the slip surface to using our analytical method. And as you can see the results, that this method can be used for different ledgers, and we can determine the factor of safety. So how we can determine the factor of safety is we have these vertical stresses, and we can compute the horizontal stresses using limit equilibrium method, which is the Rankine or Coulomb methods. And then if we use the sum of forces, we can satisfy the lateral equilibrium. After that, if we apply the stress reduction method and start reducing the stresses, the soil parameters until we find the equilibrium, that is our factor of safety. So this is our simplification. So we are using the vertical stresses, putting in a horizontal stresses, and then we can compute the factor of safety. So the idea then, the validation is done with finite element, where we can validate first the magnitude in this plot of the factor of safety, and I'm comparing here our theoretical factor of safety versus the finite element. And you can see that for these 135 cases, we are predicting well the factor of safety. There is no very dispersion, and the one comparison is very well. So this is to predict the magnitude. And also we can also predict where is the location of the lead surface and also the geometry. And I'm gonna show just for one case, and we can see that we are plotting here the shear strength in the SR in the strain reduction method calculation of Platzi's of the numerical method, and you can see that we are predicting well the even the highest shear strength that are indication of the slip surface, and the red is our method. So this gives us a lot of confidence that we are in a doing a good job. And finally, all of these methodologies are very difficult to code. So we are also having a package, a software that hopefully we are gonna start sending that to engineers for a beta version, where we can calculate for different substrate conditions, different interface properties, varying the column properties and the column geometry, analyze different field heights, and we can have the result for what is the vertical load transfer, how the stresses are gonna vary in the soil, and finally, we can have also the factor of safety for global stability. The idea also is to have, or we already have for example, optimize the column spacing to achieve a factor of safety of 1.3 or 1.1, or the field height. It could be also it's an option. So this will have a tremendous impact in engineering, because now they used to make numerical analysis, and sometimes the software is very expensive or is not available in the engineering company. But this can help to ensure that we are getting a practical solution and an effective solution. We can also make parametric studies, sensibility analysis. We are going to incorporate also an stochastic analysis. And the idea is that we can have more effective and fast, because numerical analysis is sometimes very difficult to analyze. It requires a lot of time, a lot of effort. But with this simplification, and we are getting same result of the numerical analysis, so we can have designs that are more effective and that help us, the engineering community. So I want to thank Aaron Galan for the support, and also the DFI and the TIDC for the funding. Thank you so much.